All right. So welcome, everyone. It is a pleasure to see you here. So this is the union session, Progress in Earth System Climate Science and Predictions by the U.S. Global Change Research Program. That's USGCRP, for people who are involved in this program. So I'm Anarita Mariotti here representing NOAA. I'm here with my co-conveners, Renu Joseph of DOE and Jin Huang of NOAA, NASA Constantine, who's the other, sorry, David Constantine, who's from NASA, could not be here. And this session has been organized within the scope of the USGCRP IGAM, that's the Interagency Group for Integrative Modeling, the IGAM. So for this EGU fall meeting, the World Climate Research Program, that does WCRP, has organized the Climate Science Week to celebrate 40 years of international climate science. On the occasion of this important anniversary, this session will showcase USGCRP contributions to advance Earth system climate science and predictions within the scope of individual US agency missions. USGCRP founding legislations calls for the program to, quote, coordinate the federal activities of the US with programs of other nations and with international global change research activities. WCRP has been a long-standing and important partner to USGCRP in fulfilling this mandate. As examples, USGCRP agencies have coordinated efforts and made substantial contributions to WCRP's coupled model intercomparison projects, that's the CMIPs, and also core projects such as CLIVER and GREX, among several others. These activities have been important for key USGCRP accomplishments, such as the congressionally mandated National Climate Assessment. Talks in this session will portray exemplary research milestones and projects depicting scientific progress supported by USGCRP agencies. They will include examples of process research to advance foundational understanding of climate predictability and coupling of Earth system components, the development of advanced modeling and prediction systems and their applications. They will provide overviews of USGCRP legacy achievements as well as emerging findings and opportunities in the broader WCRP context. They will help to illustrate the strategic involvement of national and international partners in the USGCRP through key agency programs. So now I'm going to pass the baton to Renu, who's going to chair the session and introduce our speakers. Thank you.
So to kick off this particular session, we have none other than Dr. Warren Washington, who has been extensively involved in both WCRP and USGCRP activities. So I invite Dr. Warren Washington to come and talk about the evolution of the world climate research and United States global change research programs. Dr. Warren Washington.
You have 16 minutes.
Okay, how much?
16.
Okay.
And 2 minutes for questions.
Hello, everyone. I'm going to give us a little bit of an unusual talk, some human factors and what happened. And as is usual, there are personalities that drive some of the programs. And oops, what am I doing here?
Use the arrow.
How do you advance it?
Wow. Escape us.
Okay, do this one here.
Yeah.
A lot of this resolved in what is the birth of the U.S. Global Change Program. Here's a book by Alan Bromley, who was the science advisor of the first George Bush administration. And he had a big influence on getting this program started. on the early development of the U.S. Global Change Program started in about 1989 under the George Bush administration. He had a chief of staff by the name of John Sununu, who was very skeptical of climate change. And so the two gentlemen had to figure out how could they sort of exist in the same administration. and they worked out sort of an agreement. Bob Carell was chair of a subcommittee dealing with the U.S. Global Change Program, or its predecessor, because the name changed in over several years. Now, first of all, John Sununu gave me a call late at night because he apparently misquoted a paper in Newsweek magazine. And I tried to correct it by sending him a telegram. What Jerry Meal and I at Ncar did was carry out I think it was the first fully coupled atmosphere and fully ocean model. And he didn't believe in the results. So he called me at home. Actually, he woke me up. And his first question was, how do you solve the equations? He said, do you use finite element, finite difference, or finite spectral? I knew this wasn't the typical White House discussion. Anyway, I promised to send him a copy of my book. He called again the next night because he didn't get there overnight. And he read the book on the third day. I guess he must be a fast reader because he was running the government and reading the book. And anyway, he made the proposition that as you warm up the ocean, more of the heat would go down into the deeper parts of the ocean. And it would take thousands of years to sort of warm up the entire ocean. I tried to make the point to him that most of the warming would take place in the upper levels of the atmosphere, of the ocean. It wouldn't go directly into the mid or the bottom of the ocean. He was very firm in his argument, so he invited me to the White House. And as he had Alan Bromley show me around, and Alan Bromley said, don't worry, Warren, he's too busy to worry about running the model. So I left it there. I had a long discussion with John Sununu, and I didn't make any headway. Anyway, he then asked me if I could install the model in the White House, and I told him that we don't have fast, that you don't have fast enough computers here at the White House. And he said, "Oh, I have a Fortran compiler and a compact 386." And anyway. We tried to dissuade him from, and then Bromley called me very quickly within a few days and said, get him off my back, get him a model. So we did generate a simple model for him to run in the White House. But anyway, it was a strange experience. I already mentioned this. My first question, and So Bromley asked Don Albritton and myself to talk to the science agencies and department in the White House Roosevelt room. The Roosevelt room is right across from the Oval Office. And at the end of this discussion that we had of giving advice, I mean, Al Britton actually talked about observations, and I talked about modeling. Now, the key to the end of the discussion was very important. Bromley asked each climate-related agency head and department head in the room if they said yes to starting a U.S. global change research program, and they all agreed. And we had a very fruitful discussion, and I think that was the actual agreement to have the different parts of the federal government come up with an overall plan. And more importantly, on this was shared with Congress, and it was put into law. And I'll show you on the definition of that in just a minute. Oops. There it goes. And the following slides were provided by Katie and Reeves and Michael Kuchenberg of the U.S. Global Change Program. As I said earlier, that the presidential initiation started in 1989. It's mandated by Congress in the Global Change Research Act of 1990, and that's really helping keep it going. And the compromises of the science arms of 13 agencies and departments with responsibilities in global change. And what they came out with basically is a comprehensive integrated U.S. research program which has lasted these last 30 years. And this plan, or this research program, had as its goal to understand and assess and predict and respond to human-induced natural and induced changes in the global change. And the agencies are all listed here. I think these are all familiar to you. I might point out that on the National Standards Agency is also part of Commerce, and so it's not separately listed. On the activities of the U.S. Global Change Program is listed here. Here we show on the left-hand side the coordination and the advance of global change research, on the use of research results and products to help inform decision-making. And that sort of decision-making is actually delivered in a very excellent way through the National Climate Assessment Annual Report, and every 4 years is updated. And we also are fostering international research cooperation, and that mostly happens on the World Climate Research Program. On the U.S. Global Change, it does not independently set agency projects, set agency budgets or priorities. Those are set by other parts of the government. Or it doesn't issue funding calls or conduct primary research, but sticks to the development of a federal policy that deals with the U.S. Global Change Program. In the 2012 and the 2021 strategic plan, we've had these four driving goals: advance the science, inform decisions, carry out sustained assessments, and communicate and educate on the public and the science community so that they would sort of work together and broaden our understanding of climate and global change. We do have some interagency groups, and I think some of these have been long-standing ones. I was chair of the Academy's advisory board for 6 years, up until 2017. And I see some of the same words. On the carbon cycle is very important: observations, modeling, human health, social sciences, international activities. Here again, on the WCRP comes in here. Sustained assessments, indicators, integrated water cycle, and adaptation and resilience. All of these are being dealt with by interagency subgroups of the U.S. Global Change Program. Here I show some examples of products. We actually have every 4 years assessments of science and impacts of climate change. On the National Climate Assessment, has a special report, and then the fourth National Climate Assessment. And I might want to point out that in the fourth National Climate Assessment, virtually all of it can be accessed through the internet. So it's very convenient to users who want to find out certain things about the climate assessment. I want to also point out that the U.S. Global Change Program and Sustained Assessment is issuing even more special reports. Here's 3 of them: carbon cycle, human health, and food security. And associated with each one of these, we have data sets and analysis and indicators. So it actually has summaries of state-by-state climate resilient toolkit and scenario products. All of these are integral parts of special reports that have meanings to different parts of the public. From 1989 to the present, there has been an active international involvement in the Global Change Program, such as the World Climate Research Program. I think that we should be proud that we have this stalwart and capable way of giving information to the public and to the policymakers. Thank you very much.
Thank you. Questions for Warren?
Over here. I can talk loud underneath the mic. What you've described is the work of the federal government on research on climate change.
That's right.
Was there a similar program to do research on solutions to climate change?
I think that's an integral part of it, and I think that they've been very open to adding to our knowledge base. How can we get into a better situation by doing various things, cutting emissions and so forth. I'm not sure that we've made that as relevant as some of the other things. And however, if you look at on the way that the funding is handled, we do have people who are looking at ideas in renewable energy sources, also in geoengineering issues. And I think this is contributing to our overall knowledge base of how to deal with climate change. Any other questions? Thank you.
Okay, there's one more. Yeah.
Oh,
Could you comment on the role of the American Geophysical Union in this process?
oh, that's a good question. I would say it's one of the major meetings that we all come together in, and that we actually try to solve some of these problems, but also give a status report on how much new information has come out that will help us make decisions on further research and how to deal with these very serious problems. So I think it's been one of the few places you can come where you can be enriched in your knowledge in all of the aspects of global change. Any more?
Any more questions? If not, let's thank Dr. Warren Washington.
Thank you.
So the next talk is by Dr. Ruby Lung from Pacific Northwest National Lab. And she is the chief scientist of the E3SM, the Energy Exascale Earth System Model at DOE. And her talk is on leveraging observations for Earth system process research, modeling, and predictions.
Okay, good afternoon. Thank you very much for coming to the session. I have this topic that actually was assigned to me to talk about leveraging observations for Earth system process research, modeling, and prediction. And
Should I be using this?
Yeah.
So clearly, observations have been used a lot in many different things. I would say, like over here, I particularly put observation in the center here. So observation is enabling, understanding, modeling, and prediction. And over the years, there have been many different platforms that have been used to collect data. So here, I like to kind of emphasize that the Earth system, when we talk about, we are talking about the atmosphere, the land, ocean, sea ice, land ice, and river. Observations are used in many different ways. Maybe I have missed some here, but I think that it probably covers quite a lot of the uses of observation. So first of all, observations are used to discover and characterize Earth system phenomena. It's also used to improve understanding and develop theories. It can be used to monitor and identify Earth system changes. It can be used to inform development of model parameterizations. And then, of course, we want to use data to evaluate the parameterizations and the models as well, including the use of instrument simulators. And then data can be inputted to models, and including the use of data as simulation. And then data are also the critical part in terms of developing reanalysis products. And then they are used to initialize and improve predictions, and then also can be used for constraining future projections. So I'm going to give you examples of these uses of data. Particularly since we are talking about the Earth system, I don't think that I can use like 15 or 16 minutes to really cover all of that. So I'm going to give you examples, particularly related to the water cycle, which I'm a bit more familiar with. And also, I'm not trying to really provide a historical perspective covering 40 years of use of observation data. So most of my examples would be coming from studies that are in the past 10 to 15 years or so. So the first one, so the way to read my slides, essentially I'm telling you what the examples are. So this one is an example of discover and characterize Earth system phenomena. So one use of observation data has been to use the SSMI satellite images of integrated water vapor, which we can now then use to observe the atmospheric rivers on scale covering over the oceans. Right? So this is difficult to do if we fly an airplane across, but with satellite data, this can definitely be done. So this is one way, a good use of observation data from satellite. Besides satellite data, in terms of studying atmospheric rivers, we have also have field campaigns where we involve multiple aircraft and also using even like shipborne instruments, etc., to really quantify the role of atmospheric rivers as well as the impact of aerosols in how they might be modulating precipitation over the western United States. So some of the examples of studies that we have done include like using the data to really constrain the moisture budget of atmospheric rivers and improve understanding of predictability. We have also quantified and identified the role of long-range transport of dust that impacting atmospheric river precipitation. Another use of data is indicated over here, improving understanding and developing theories. So this is a field campaign called Green Ocean Amazon. We call it Go Amazon. So in this field campaign, there are multiple instruments located in different areas, but the center location is in this Manaus, basically a city in the middle of a pristine rainforest. So essentially here, major observations that have been used to really identify the substantial role of ultrafine aerosol particles and how they are affecting convection and precipitation. So the type of measurements, particularly updraft speed, and also the size resolved aerosols, particularly these ultrafine aerosol particles, have been identified to play a significant role in terms of regulating convection in the middle of the Amazon tropical forest because of these fine ultrafine aerosol particles emitted from the city. Another use of data, as I mentioned before, is to monitor and identify Earth system changes. So this is one example of using the GRACE data to really identify there have been substantial long-term trend in terms of the decline of groundwater table in India. So in this figure, the groundwater withdrawal is shown here as a percentage of the recharge. As a result of the groundwater withdrawal, the GRACE data has identified this long-term trend in the groundwater, indicating a significant impacts of groundwater withdrawal for irrigation has an impact on the groundwater table. Now I'm going to give you some examples of how data is used to inform development of model parameterizations. So in this particular example, they are using data from the southern Great Plains. So over there, they can calculate the CAPE, which is essentially what we call the convective available potential energy, the amount of energy which is both the heat in terms of temperature and the moisture that is needed in order to produce convection. And based on the observation data, they find that the change in the CAPE is mostly controlled by the CAPE changes within the planetary boundary layer rather than the large-scale circulation. So based on this information, they were able to improve convection parameterization in climate model, and as a result, they were able to better predict the simulation of simulate the IDCC location and the intensity. Another example is to use data to evaluate parameterizations. So we do use data a lot to evaluate models, but data such as collected in location like, for example, the Southern Great Plains, they really provide you with many different variables. Like in this example, the authors were able to use multiple data coming from like Doppler radar, in situ aircraft, radar data, dysdrometer, sounding, etc., etc. So this is allowing them to really identify what are causing these biases in precipitation in these mesoscale convective systems that they are simulating in their model. So in this system, they were identifying area where there are deep convection, as well as area where there are stratiform cloud, and then they identified that in this convective area, there is an over-prediction of precipitation intensity, partly because of the biases in the cold pool and the latent heating. But then in the stratiform area, because of these multiple data set, they were able to identify that there is an underestimation of precipitation, but it is due to the vertical profile of the ice water content. So this kind of information is really important for us to not only say that the model has problem in simulating the precipitation, but in what particular aspects the model is really having deficiency. Now another example, also using data to evaluate parameterizations. So when we talk about satellite data, oftentimes it's not that easy to use satellite data to evaluate our model because you have to go through retrieval of the radiances coming from the satellite sensors, and then you convert that to variables that your model actually simulates. So in some sense, you are sometimes comparing apples with oranges. So there have been development of these simulators. So simulators that actually take model output and then convert the model output into something that the satellite sees. And then you can have a better apple-to-apple comparison. So with this kind of simulator, now you can compare your model simulation of many different aspects of cloud, compare with many different satellite cloud observation products, including from the ISKIP, CloudSat, and Calypso. So now this kind of simulator is often used in many major modeling centers to compare their model simulation of clouds with observation. So one example is just shown over here. Another example is how we use data to initialize and improve predictions. So in this particular example, we are talking about the prediction of Ensemble. So this is using the GFDL CM 2.1 model. Lots of data are being ingested into the model to improve prediction of Ensemble. So in this particular example, you can see the comparison of the model simulation with the data if you ingest all kinds of data available to you. And then you can start removing some of the data and run your experiment again and see what data set are most critical for improving the prediction of Ensemble. So in this case, you can see if you remove the Argo data, then there are significant differences between the model simulation and the observation, suggesting that Argo data is really playing a very important role in improving our ability to predict Ensemble. Another example related to prediction is to look at the hydroclimate of the Western United States. So here you can look at, like, for example, 2 different winter seasons between 1997 and 98, and then 2015 to 2016, showing you the observed precipitation anomaly in the top, and then the prediction when you only use ocean initial conditions to help you predict the precipitation anomaly, versus in the bottom where you are predicting the hydroclimatic or the precipitation anomaly using initial condition from ocean, atmosphere, and land. So you can see the importance of these various types of data that are being ingested into the model as initial condition for improving your model prediction. Now going to the last topic, here we are interested in how data observation can also be used to constrain future projection. So as we know, we use climate models or Earth system models a lot to project into the future, how the temperature will be changing, precipitation will be changing. But of course, there's no way we can actually evaluate whether these projections that might be like 50 years or 100 years from now, whether these projections are actually making any sense or whether they are accurate or not. But one way that we can do this is really to develop relationship. For example, here, these studies show that this warming, we can call the equilibrium climate sensitivity when you project into the future. The warming has a lot to do with the cloud feedback represented in your model. For example, if your model suggests that under global warming, the low clouds, such as stratocumulus clouds, will be disappearing, then it can cause more solar radiation to go through and further warm up the Earth. So that would be a positive feedback. So there's a pretty strong correlation between the two. So now the question is, but what should the cloud feedback be? So in this particular study, they listed all these observation inferred cloud feedback. And so based on that, you can also look at your model simulation to see which model projection would be more aligned with the observed cloud feedback and therefore the credibility of the future projection of the climate sensitivity. Another example, this is the last example here, we can also use observation data to do a similar thing, but here we are focusing on projection of the hydrological cycle, how the global mean precipitation will be changing in the future. So as we know, precipitation is pretty much governed by a surface energy balance in terms of the latent heat and then the long wave and the short wave radiation. So uncertainty in your model simulation of the short wave absorption when there is more water vapor under a global warming scenario would be affecting your model projection of how global mean precipitation will be changing. So in this study, they did find a really tight relationship between how the short wave absorption as a function of the precipitable water, the increase in the water vapor due to temperature, having a close relationship with the clear sky change in the short wave radiation as a function of temperature. And as a result, you can put the observation over here. So based on observation data such as the Sirius EBAF solar fluxes and also the SSMI water vapor, then you can identify where the observation should be and therefore which model projection would be more believable in terms of the changes in the global precipitation. Further, in this study, they also identified that if you look at all the radiation schemes being used in the model, they can actually identify that newer schemes that are developed like in the recent decade or so, because they use more spectral bands, they tend to be more realistic in terms of actually simulating this dependence of the solar absorption as a function of the precipitable water, and therefore maybe these models do have a more realistic projection of global mean precipitation. So lastly, I just want to say that there is an emerging class of global cloud resolving model where we are now able to run simulation globally at really high resolution. So with this kind of tools, there is an opportunity to really make use of observation data such as shown over here from Himalaya, where you can really use high resolution satellite data to evaluate your simulation. So now I'm just going to put up a slide, the last slide, kind of discussing a little bit about future directions. I'm sure that I'm not covering all of them, but I think some of that could be I think we still need a lot of field campaigns because they do give us many different variables that we can use to improve understanding. But I think future field campaigns can really look at not only a single component like the atmosphere or the ocean, but multiple Earth system components, and the interaction would be really useful. We also need more measurements of fluxes across Earth system components, like the fluxes between the atmosphere and land, and between atmosphere and ocean. We need to develop strategies for increasing the spatial temporal coverage and the measurement of multiple variables. So satellite data is great, but for example, satellite data such as TRIM data or the GPM data, they do have an inclination angle, so the visit time is actually quite infrequent. So we need to develop strategies for addressing this kind of limitation. Development of sensors, use of unmanned facilities like drone. We have now drones for atmospheric measurement, as well as sail drones for ocean measurement as well. Miniaturization of instruments, maintain and expand capabilities for continuous monitoring of Earth system changes. We really need to continuously monitor the changes. We have great satellite data that have helped us to really monitor the Earth, but some of them discontinue, will really not allow us to continue to know what is happening in the future. Finally, I think there's also need a lot of efforts in terms of synthesizing all types of data that we are collecting from field campaign, from ground-based measurement, from satellite data. So once we synthesize the data, I think it would be a great use for data discovery or use of machine learning or artificial intelligence types of studies to really help us improve understanding and prediction. So thank you very much for your attention.
Questions for Ruby? Yep. Can you use the microphone, or can you speak loud enough? Thanks.
Thank you very much. That was an amazing presentation on such a general topic. I appreciate it.
Thank you.
Are you familiar with the efforts to prioritize continuity of observations? NASA has asked for sort of efforts to do that. and associated with the decadal survey. So some groups have come together to try to produce a quantitative value to what observations should be continuity or continued. Do you have any comments on that?
I heard about this activity, but I cannot say that I know too much about it. I think it is a really valuable activity because, after all, we know that we are all operating under limited resources, so we have to prioritize. So when we prioritize, it's better for us to really understand what's the value of each of these different types of measurements that we can make to be better informed about the decision for the future. Yeah, thank you.
Any more questions? So just one question from me. In order to better understand the water cycle processes over the US, if you were to organize a campaign, what kind of a campaign would you look at?
Yeah, if you're talking about the water cycle, I would really love to have a campaign that we can really make use of platforms that allow us to look at interactions. Because I feel that in the past, a lot of field campaigns focus on a single component. But we have a lot of lack of knowledge about the planetary boundary layer, for example, which involve measurements not only for the atmosphere, but also the surface fluxes and the states of the land surface. So I think these type of field campaigns would be very helpful for water cycle type of questions. Yeah.
Okay. Thanks.
All right, thank you very much.
So next our next speaker is Dr. V Ramaswamy, and he's the director of NOAA's Geophysical Fluid Dynamics Lab, and he's also one of the principals of the US Climate Modeling Summit. So,
Okay. Good afternoon, everyone, and many thanks to Renu and Anarita, as well as to Jin and David for giving me this opportunity to present to you some perspectives on how we have traveled from the past to the present to the future, research advancing the Earth system modeling in the US. So this is not going to be comprehensive, just like Ruby said, but it's going to be mainly snippets, but hopefully capture some of the highlights of the story. So first of all, I think Warren mentioned this in his talk. Under the US Global Change Research Program, there is the IGIM, which is the Interagency Group on Integrative Modeling. It is one of several working groups of USGCRP and consists of representatives from different agencies with interest in climate and Earth system modeling, and is also making investments. And then under the IGIM, we have the Climate Modeling Summit, which is a group tasked to enhance coordination, working towards a common national climate Earth system modeling strategy. And this group actually meets annually. The idea in this group is that the modeling centers engage in discussions on major objectives and difficulties and challenges. And the agency representatives present the current priorities and directions and issues at the management level. And then there's dialogues on how we might improve strategies to further the US climate and Earth systems, Earth science mission. Now, just to have a couple of points on what the scope of this talk is going to be about, just a few principal activities of these climate modeling centers. There are 6 of them. And primarily the talk is going to concentrate on the reduction of biases and the 20th century simulations using for CMIP6. And then some few examples of the contributions where the Climate Modeling Summit centers have been interlinked with international modeling centers and WCRP, including the CMIPS and the IPCC assessment. So I'm going to go through each center rather quickly and try to display to you some of the important things that have happened in recent times. So first in NOAA, there's been this generation of this FE3 atmospheric dipole, which now forms the basis of all of NOAA's models, as well as NASA's atmospheric models. And the twin goals of this are to develop a unified modeling system for weather and climate predictions, and to unify regional, that's convective scale, and global modeling systems. And now this is sort of the forming the basis of the operational forecasts. On the other front, there is the Modular Ocean Model version 6, and which is capturing the ocean, which is doing the ocean component in both Ncar, in NOAA, as well as it's going to be used at Ncar, and is being tested by the US Navy. And sort of two things which have advanced ocean modeling now are trying to capture the role of ocean eddies in the climate system, and also the interactions between oceans, and ice sheet ocean interactions, which kind of govern sea level rise. And this is really hot off the press from NOAA's Unified Forecast System, seasonal prediction of the sea ice extent in the Arctic and Antarctic. So this uses initial conditions and predicts the seasonal cycle, rather remarkable resemblance to the actual data. So this is actually a very good forward step, and it's one of the first version of the kind, and the later versions probably will be even better. Turning to NASA GMAO, this is something that the GMAO has done a remarkable job in terms of slowly increasing resolution of the model, and then in the end, coming to the 3-kilometer GEOS model, which one of them was displayed on Ruby's slide earlier. And the idea is that you can catch, for example, the IR emittances from the planet and capture them in a way that you can actually compare to satellite data, which is shown on the bottom right. So this is really a significant advancement in recent times to depict on the cloud scale, convection and other related variables in the model. And carrying this further, GEOS is now able to do, for the first time, a high-resolution global real-time system of chemical composition using 250 reactive gases and parallel schemes for aerosols. Again, sort of a really very encouraging recent development. Turning to Ncar, so Ncar has, and then you'll find that in the subsequent slides also, a lot of centers have concentrated on reducing biases. In the case of this particular slide, it is the reduction of biases in the shortwave cloud forcing, and the bottom two panels and the top right panel, when you compare them with the observation, the series observations shown on the upper left panel, shows a significant reduction of biases, and these improvements are largely due to updated microphysics and better representation of low clouds via the club parameterization. And this is the simulation using the latest model of the global mean surface temperature time series, and both the two models here, the vacuum and the CAM, compared with the observations. And you can see that they actually resemble the historical evolution rather nicely, except the last 20 years, which is kind of a bit of a syndrome with all models. They warm up more than the observations, something which every center is still trying to understand. Turning to DOE's E3SM, they kind of have, the model shows similar issues with regards to the warming that's simulated by the model compared to the observations. And this actually now has been analyzed in detail, and it turns out it's due to the essentially the aerosol-related effective radiative forcing, which then kicks in a high shortwave cloud feedback and pulls this towards the high end. And then one of the things that is, again, common to all centers, exemplified by this plot from E3SM, is the global cloud resolving model at 3 kilometers grid coupled to an eddy resolving ocean model, as well as multi-scale modeling, such as embedding the cloud resolving model in the E3SM, and something that is going to be a challenge for all modeling centers, which is the exascale computing strategies and adapting to modeling on exascale machines which have hybrid and largely new architectures. GIS has also gone into pay a lot of attention to introduction of cloud biases, and this particular plot shows how the parameterization based on satellite observation has improved from the distribution of particle size in the old model to the new model, conforming much better to the observations. And this is, again, making use of the observations that have been accumulated in recent years and which are proving very valuable. In GIS's case, they actually get a very good simulation of the 20th century temperature change. And one of the interesting things is when they analyze that, they actually show that it's a combination of both the forcing update as well as the model physics update that is actually helping them to capture this 20th century very well. In the case of GFDL, some of the model improvements, some of the models that have come on board are the climate model version 4, Earth system model version 4, which has couples the biogeochemistry with the physical climate model, and then the sphere model, which is actually an offshoot of CM4, but is used for predictions from seasonal to decadal. And in this case, you see the MJO eastward propagation coming out very nicely. And then the major sort of effort in going from models from 2005, which was for CMIP3, then CMIP5, which was circa 2013, and now CMIP6, you see the systematic reduction of biases, largely due to improvements in the observations, the availability of observations, and also fundamental theoretical developments. And in the case of the GFDL model, just kind of going to the table here, the climate sensitivity turns out to be 4.9 according to the full integration with a full coupled ocean. Whereas the Earth system model actually gets a lower sensitivity, which is very interesting that the interactive chemistry and biogeochemistry feedbacks are conspiring to give a lower climate sensitivity. This is kind of still being actively pursued as to exactly what the causes are and whether they're robust. So now let me turn to some examples of collaborations and partnerships. Ruby mentioned some which involved the modeling as well as observations, use of observations and models. I'll take an example from the 1990s, which was sort of very interesting when this happened, that the long-time integrations were done for 3 different models, by 3 different modeling centers, Hadley Center, GFDL, and Hamburg. And the idea was to see what the internal variability in the model simulations was. And one of the things that this helped prove was this observed change from the pre-industrial to present could not be explained due to internal variability, because internal variability in all these models was very small, was much smaller than the actual change that's occurred in the last 150 years. So also there was realistic variability on the shorter time scales, which established a little bit of the fidelity of these models to actually simulate internal variability. And now, of course, there's been vast improvements in terms of the internal variability as well as the modes of variability. We have had climate process teams which have been very, very instrumental in advancing parameterizations in models. They brought together observationalists, theoreticians, process modelers, climate model developers, and everyone has had to suppress their egos to actually work together and work on improving representation of particular processes, which has actually had a very interesting outcome of reducing biases. And some of the biases you saw reduced in the previous slides are actually due to data from climate process work. And the idea is, of course, that some of these actually have spawned other CPTs. And now there's actually a particular CPT on the oceans which is looking at the eddies in the ocean. So this is, again, something which has come out of the interagency work, interagency thinking on this idea. Now, an outcome of the recent Climate Modeling Summit held in March of 2019, is a sort of joint analysis of the modes of coupled climate variability in the US climate models. And this is, the top panel is for the Nino 3.4 variability, bottom one is specific decadal oscillation. And if you look at any of these panels, let's say 6 to 10 years, the observations represented by these dots, and then these are all different models. And then there's a CMIP5 representation of these same models back in the CMIP5 days. And what you see is actually a gradual improvement in representing these modes of variability across these timescales. And this is actually going to be submitted to a journal, and it's going to be very interesting to see kind of how not only the US model, but then how the other models in the world fare under this kind of comparison. So let me now take you to a major lingering uncertainty. So we think we are kind of solving all problems and heading in the right direction all the time, which is true, we are heading in the right direction. But this is lingering uncertainty. CO2 radiative forcing. So this is now a paper from Bob Sess's really seminal work in 1993, getting various models and trying to analyze the double CO2 forcing. And the range then was 3.2 to 4.8 watts per square meter, which again was at the time of the IPCC, the first IPCC report, 1990. Well, now we are, let's say, 2018. This is from Brian Soden et al. Science paper. And if you look at this set of, well, this is the SES era values. Now this is the values that we have here, and these triangles are, The triangles are the line-by-line results. So that's kind of where the models should fall. These are all GCM models, GCMs. So you see the range again, and if anything, it has actually widened. Now, there are more models, of course, but this is a little bit embarrassing and also discouraging that we can't do 2 times CO2 and get GCMs to agree. This is kind of a fundamental thing that we should get right. Now, there's an interesting twist to this that after Bob Sess's work appeared, over the course of the next few years, there was a social pressure to offer all the models to get closer together to the line-by-line benchmark calculations. But it looks like now, again, there's divergence, and I think some discipline has to be brought back into this particular calculation. So that brings me to the last slide, which is some kind of an optimistic look into what kind of advancements we can expect in the next decade in modeling, understanding, and projections. So one of the things is, and then going sort of piggybacking on Ruby's talk, is capturing the science of the climate system as presented by the observational evidence, but capturing them appropriately in the models. And in particular, the energy and hydrologic cycles are very important components, and they go together. They're not separate. So that is going to be very important. And then the interaction and feedbacks between the physical climate system and the biogeochemical systems. I mean, what kind of does it do to variability, change, and extremes as we look across the diversity of variables? Then the detection and attribution of changes and increasingly events even in the climate system. This requires a better understanding of all the natural variations, MJO, ENSO, and so on, but also the force changes in maybe even the variability. And then with the help of the high-resolution models that are coming along, increasingly not just atmosphere, but coupled models, global to local predictions and projections are going to be very important, especially for societal purposes. And finally, the last point is something that the USGCRP, IGIM are very focused on, and that is the continuity of the entire modeling system from weather to climate, seamless weather to climate modeling system. So with that, I'll end here. Thank you very much for your attention.
Questions for Ram?
So I'm here. I will ask the first question. Yeah, I'm Hubert, University of Arizona. We have 4 climate models supported by 4 agencies in the U.S. My questions are, first, what's the metrics for success 10 years from now for the climate modeling enterprise? And second, we have been doing this for a long time. Are we going to follow the same way, further developing 4 models for the enterprise, or it's time for a change, for something different?
Do you want me to answer that? I think, well, there's a lot of points in that question, and there are a lot of questions there. I'll just say that, consistent with the NRC 2012 report, the National Research Council, which went through this issue of the several models in the U.S. and argued for and differentiated the models according to various tiers. It didn't say anything about like prioritizing, but it did separate the models into different tiers, which support the different missions of the different agencies. And the issue, the thing that came up before them is that there is not a single model at that time, this is 2012, a single model at that time, that is something that can represent the missions of all the agencies. Now, can we get there? Perhaps we can, but I don't think we are there yet. But the other thing is that, one of the things that the observations are doing is actually forging a path towards consensus on many aspects of the models, whether it be by components, atmosphere, ocean, land, sea ice, land ice, or whether it's the issue that you brought up, the metrics that we have to look at in order to see what kind of best fits. So at the moment, I think every agency, and then there are program managers here, they can also speak to this, but at this time, the agencies are looking upon the models to deliver something that is going to meet their objectives. I think at some level, at some point, the agencies themselves have to kind of decide at a very high level, at the management level, as to what do they need from a model, and then perhaps, there can be much more convergence. But till then, I think it is going to be a path where everyone is exploring and trying to just get to a better understanding and a better representation of the Earth system. So I don't know if I answered the question all the way through, but it's a very valid question. A lot of valid questions there, and we need to answer them. Right? No question about that.
In seismology, we've developed a formal process for evaluating earthquake forecasts, and we require prospective models developed in a way that they can be tested against data that haven't yet been collected. I think you have a very similar situation that you have different models that have different physics in them and different ideas. Do you have a formal process for testing and a formal process for stating the models in a way that they can be tested in the future?
Yeah, I think this climate modeling summit that was started 5 years ago, I think, has slowly got the modeling centers to think jointly about these issues. And so, for example, one of the papers the first paper that came out of the joint venture by all the modeling centers was all on tuning of models, because at some point you don't have the data on all the physics and chemistry. So you got to tune the models to get it to simulate a reasonable climate, present-day climate. And to do that, you have to do what's called tuning, but it's actually, if you want a better word, optimization of parameters. So the modeling centers actually discussed as to how each one was doing that, and there's actually a paper in the journals which actually describes that. The second one is something that I put up a slide on modes of variability. So how are the models simulating the natural variations that are seen? And this is the first time that the modeling centers have put up their models, and one can intercompare as to how one is better than the other, or one is doing representing parameters in a much better way if you look at all the whole set of parameters rather than one single parameter. So that's coming along. So I feel that the momentum has been set to actually get into this mindset of evaluating through common metrics and not just one single metric. And in this regard, the CMIP6, which stands for the Coupled Model Intercomparison Project, is also helping, because they actually, in addition to model data sets being collected, also observational data sets are being collected. And it's not restricted to just the modeling institutions. Anyone can tap into this data and then do their own analysis. So I think it's moving along. It's chugging along, maybe moving at a gentle pace rather than an accelerated pace.
One more question,
Yeah,
or two more rather.
Okay. Yeah, I'd like to ask a question about how U.S. climate modeling centers think about the climate models as a tool to understand the Earth or climate systems, because many models are going to very complex and high resolution. Both of those aspects make it really even more difficult to conduct, for example, numerical experiments and analyzing, because large volume data, it takes more time to understand. And then also, my generation, maybe students in early career, as given complex model as sometimes kind of black box. We run the model and analyze the model without knowing too much about what's being done inside. And I just wondering, so it's obvious it's very good tool to provide projections for the decision making, but also it's tool to maybe for us to understand. And so I'm just wondering, what is your overall view about models in this aspect?
I actually think it's a very important aspect of modeling, that not only do we build these complex and high resolution models, which is kind of gets us better to representing the Earth system, but it's also equally important to develop a hierarchy of models where they can be used as simple tools at the postdoc level, graduate student level, so that they can be used to understand on a much more simpler basis. That still is a very nice way to understand. So I am all for actually developing this hierarchy of models. I think one of the things that in mission agencies have to wrestle with is the balance of time and resource. Where should they spend it? So in this regards, I think there just has to be greater partnership with, for example, the academic sector and increasingly even the private sector to actually develop these simple tools. I fully agree that you have to develop these simple tools, otherwise we keep getting complicated and complicated, and sometimes we don't understand the models ourselves, or it takes years to understand the models.
Just one more question, and I'll take
Thank you very much for this enlightening overview and analysis. Can you please briefly comment on a new development which is called EPIC, which to my knowledge is being championed by NOAA and Ncar, and which could provide something to the effect of which previous speaker was talking, a cloud-based, maybe group interagency, a new generation of the Earth system model. So how is that being viewed, and is there any perspective for the interagency collaboration there?
So EPIC, in a way, is still under development in terms of its whole framework of objectives. I'm not an expert on EPIC, but I'll say you this, the EPIC has already started. If you consider the new generation weather forecast model, GFS V15, which has the FE3 die-core, improved microphysics, and improvement in a lot of things, is giving improved skill scores right now relative to the older forecast system. In a way, that is a start to EPIC. I think increasingly attention has to be paid to other aspects of model, like data assimilation. So EPIC has that under its purview, improving that. And there are many other things. So EPIC is starting on weather timescales, and then this coupling with the ocean that has taken place and giving some very nice initial sea ice predictions. I think these are all steps towards whatever EPIC is framed as. And included in this is also things like the cloud idea, that there'll be a lot of there'll be modeling and data that can actually reside in the cloud, so that it's easily accessible to anyone outside, for example, of NOAA, and also the invocation of artificial intelligence and machine learning in the process. But these are, right now, I think there are a lot of ideas about it. They just have to be cemented towards a framework, which I don't think is available yet because it's still under discussion.
So the next speaker is Christiana Stan. She's an associate professor at George Mason University and has been extensively involved in many WCRP and GCRP activities. Her talk is Research to Address the Weather-Climate Continuum.
I would like to thank the organizers for the invitation to present some of my work that has been guided by the broader objectives of science objective of the USGCRP. And this work would have not been possible without the support of the all the agencies that actually participate in or some of the agencies that participate in the USGCRP program. So in my talk it's related to the representation of cloud processes in the Earth system models, with an emphasis on the role of the USGCRP in involving the S2S community. Since recently WCRP extended their time scales into this subseasonal to seasonal time scale, I think USGCRP is also committed to extend the time scale covered by the research to the S2S time scales. And I would like to conclude with some perspective on future USGCRP priority needs for advancing the improvements in the representation of cloud processes into these S2S endeavors. So this slide shows the list with the current methods used for the representation of atmospheric convection in the Earth system models. And 20 years ago, probably or so. This list was much shorter, and I think there was actually no list because at that time there was only one method available for the representation of atmospheric convection, and that was the conventional parameterizations. So in the last few years, stochastic parameterizations have been successfully implemented in both climate models and forecast systems. And the last three methods that include the global cloud resolving models, the machine learning parameterizations, and the super parameterization are mostly used as research tools, with the machine learning parameterization being an emerging and promising player. So most of my research is related to using the super parameterization, and I would like to take a minute to explain to you what super parameterization is. So in the super parameterization method, the moist convection in a global atmospheric model in each grid column is represented by a cloud resolving model. Depending on the available resources, this cloud resolving model can be three-dimensional or two-dimensional, like in this schematic. And the domain of the cloud resolving model is periodic in the zonal direction. And the surface forcing and boundary forcing and lateral boundary conditions come from the host GCM. And the cloud resolving models supply the temperature and moisture tendency to the host model at the center of each grid box. So modeling cloud processes in Earth system models, it's a very challenging task because of the wide impact of clouds in the weather climate continuum. And like I mentioned in the beginning, recently the time scales between the weather and climate, referred as to S2S time scale, have gained a lot of interest because these are the time scales where the sources of predictability related to the initial conditions transition to the sources of predictability related to the boundary conditions. And also the S2S timescales lie at the intersection where clouds play have a lot of influence on various phenomena. And here is just a list of them. And in my presentation, I only be able to scratch the surface of atmospheric teleconnection, something that I spent some time looking at, and also is a strong source of predictability for these S2S timescales. And this schematic shows just gives us an idea of atmospheric teleconnections. And as we can see here, from very small perturbation of cloud systems to the intraseasonal oscillations of the tropics, associated changes in the diabatic heating perturb the circulation in the overlying atmosphere and induce these teleconnections that can affect remotely occurring events such as weather events like atmospheric rivers, and all the way up to modes of variability of the mid-latitudes. So as you heard in many talks during this week, these atmospheric teleconnections are influenced by both the variability of the tropics and also by the variability of the extratropics or the mean state of the extratropics. So to get an idea of how representation of cloud processes influence the simulations and prediction of atmospheric teleconnections. Here in this slide, I'm showing a climate simulation with I'm showing results from two experiments. In one experiment, the atmospheric convection is represented using the conventional parameterization method. And in the second experiment, the atmospheric convection is represented using the superparameterization. So on the left here, I'm showing results for the climate simulation, and on the right, I'm showing results for the for a forecast experiment. So the green line here corresponds to the MJO amplitude in observations, the blue line to the conventional parameterization, and the red line to superparameterization. And here we are looking at two locations, one in the Indian Ocean and one in over the Whirlpool region. So very easily we can see that the superparameterization simulation aligns much better with the observation. And when we look at the forecast, again, we see that the forecast scale of the superparameterized model shown here in green is much better than the forecast scale of the conventional parameterized model. And another metric that we like to look at this for the MJO is the MJO phase error, and we see that the model with superparameterization has a slightly slower propagating MJO, whereas the model with conventional parameterization has a much faster MJO than in observations. And this result is actually consistent with what we see in the climate simulation, where we see this large shift in the phase of the amplitude of the MJO. So now, since I mentioned that atmospheric teleconnections are influenced by what's happening in the tropics, let's see an example of simulation of the atmospheric teleconnection in the extratropics. And here I'm only looking at the simulation of the NAO, both phases of the NAO. The top panel show the NAO plus, the lower panel show the NAO minus. And again, the results for the conventional parameterization and superparameterization. And to very quickly summarize the differences between the model simulation and the observation, I'm showing here the pattern correlation between the models and the observations. So again, we see much better agreement in the superparameterized model than in the conventional parameterized model. So we have seen the results in the simulations. Now let's see if again these improvements that we see in the simulation translates in the improvements in the forecast scale. And you know, this is a busy slide, but I am actually what I am showing here is the 500 geopotential anomaly after calculated during the a particular configuration of the tropics, which corresponds to convective activity located over the Indian Ocean. And this is at 1 week after, 2 weeks, 3 weeks, and 4 weeks after. So to keep this slide readable, I didn't put observations here, but again, I show the pattern correlation between models and observation. And again, we see a larger scale in the superparameterized model that we see in the conventional parameterized model. So it turns out that these problems that we see here tend to affect most of the forecast model used for the used by the operational center for the subseasonal to seasonal forecast. And I just want to give you an example here on how this model do. And I'm showing a case study, which is the Eastern Canadian flooding event that took place in the spring of 2017. So it was established that this flooding event it was caused by the rapid snowmelt and also heavy rainfall that happened during the first week of May, as is shown here by this precipitation anomaly for this week. So when we look at the the pattern of the large-scale circulation corresponding to that week, we see something that resembles the NAO minus that I showed earlier, which can be related to the convective activity in the tropics during April. So now let's take a look at how the S2S models are doing in forecasting this precipitation anomaly on the left here. And with the exception of two models that forecast a dry anomaly rather than a wet anomaly, most of them actually capture the wet anomaly 2 weeks in advance. So this is the forecast were initialized 2 weeks prior to the event, but the amplitude of the anomalies is much smaller than in observations, and there is actually only one model, this one here, that forecast the precipitation anomaly with an amplitude larger than 30 millimeters per day. So now when we look at the forecast of the large-scale circulation here on the right, we do see that the models are also all over the place. And this model that has a good forecast skill for precipitation also has a large, a high value of the correlation pattern. It's not the largest one, but it is relatively high. So now looking back at what's happening in the tropics at the MJO, if we look here in this diagram, we do see that most of the models forecast that 1 week after the initialization that the MJO is in phase 7, but they are a little bit all over the place. And in general, we see that most models tend to forecast a slower than observed propagation of the MJO, and the correlation, again, it's shows a large spread. So as I mentioned in the beginning, this teleconnection also depend on the what's happening in the extratropics, and using the super parameterized model, being confident in the ability to simulate the convection in the tropics, we were able to conduct some experiments, and we found out that the subseasonal variability of the extratropics actually affect the probability of the landfall of atmospheric rivers that reach the west coast, and also the latitude where the landfall happens. So with this, I just want to conclude that if we assume that the S2S timescale represents the bridge in the weather climate continues, then we can say that clouds processes are among the most important ingredients paving this bridge. And if how we can continue to do this is by carrying out climate modeling and reforecast experiments with parallel methods for the representation of cloud processes. And climate simulation will allow us the exploration of scale interactions in this weather climate continuum. And the reforecast experiments will test the sensitivity of these methods to the initialization algorithms. And I also think that in addition to the the field campaigns, the observational field campaigns, we should also carry out virtual field campaigns in all of these high-resolution model data that are being produced. And to do that, we need to develop tools to extract virtual observations from these high-resolution model data sets. And we also need to develop diagnostics that mimic these field observations. So, thank you.
Thank you. Questions for Christiana? Okay.
Just, I would like to ask you, you have a whole range of possibilities to define your subgrid scale model. And how do you choose the specific model you want to use, or how do you validate it, in fact? Because a whole range of models you can use at the subgrid scale.
Well, this is what I am actually advocating for, that these parameterizations be implemented in more than one model, because what I presented here is based on one model, and maybe it's something particular about this model that gives us these results, but if we do the same thing with other models, and it's actually being done, so I think we've seen results from 2 presentations that the super parameterization is being implemented in other models.
Okay, thank you, Christiana. Now the next talk is by Ben Kurtman. He's a professor and director of the Cooperative Institute for Marine and Atmospheric Studies at the University of Miami, and he's been extensively involved in sub-X and anemone experiments. His talk will be about research and development of climate prediction systems.
While Renu is getting that set up, I want to, of course, thank the organizers, and all of you for staying. And I want to thank Warren for that really nice story about giving John Sununu a climate model. And I was just kind of thinking maybe we should offer to give Mick Mulvaney one, since he's the acting chief of staff now, and maybe he would ask some questions about, spectral method versus finite volume methods and solving those equations. So I'm going to talk about research and development and climate prediction systems. Everybody can hear me. One of my character flaws is I'm fidgety, so I'm going to drift away from the microphone. I can't help it. It's part of the character flaw. Research and development of climate prediction systems, but what I really want to call it is really how the WCRP, in part through International CLIVAR, and USGCRP, in part through the US CLIVAR, enable climate prediction science. So that's really what I want to talk about. So here's the pictures of US CLIVAR superimposed on the USGCRP. So I went to obviously I Googled last night. And one thing I did notice, did you see this, the picture? These are 2 totally different independent websites. Look how similar the picture is. The sunset there, very, very telling. Okay. So, yes, very well coordinated. Thank you. Very well coordinated. Okay. So research and development in climate prediction systems, and I can add to this laundry list of issues that we are grappling with today. This is probably the same laundry list of issues that we were grappling with 10 years ago. We're getting better at them. I think that's what Ram told us, is that things are marching forward, things are improving, but we're impatient and we want more progress. The one thing, if I had to think about what did WGCRP, what did USGCRP, what did WCRP, what did US CLIVAR, International CLIVAR really bring to the table from my perspective, and that is really facilitating multi-institutional, multinational, multi-model coordinated numerical experiments. So they really set the framework where we could design and implement numerical experiments to test hypotheses together. And that's a profound contribution. That's something that perhaps we forget about all the time. So I want to talk a little bit about how that profound contribution has actually pushed climate science forward, climate prediction science forward. So one of the multi-institutional, multinational, multi-model projects was this so-called Climate Historical Forecast Project. And what this picture shows is just showing you how well these models predicted the past, the sea surface temperature in the tropical Pacific. So this is sort of how well do these models predict El Nino going out to 7 months. The black curve is an RMS error. How well do the models match up with observations measured by the root mean squared difference. The red curve is an important curve. These are ensemble of predictions. So this is an ensemble of models that are making an ensemble set of predictions. And so those red curves are showing you how those models spread, how they spread over time. And if those models spread at the same rate that the error grows, same spread and error, if they line up with each other, we have a well-calibrated system. I can say that if I know the forecast spread, I can make a forecast of what the forecast error would be. And that would be a powerful tool. And what you notice is with each independent model, none of them are on top of each other. So either the models have too much error or not enough spread independently. Okay, well, there's one box in the bottom corner there. That's the multi-model ensemble. So if I had to drill down even further into my arena of subseasonal to decadal prediction, it would be this notion that multi-model prediction improves both, reduces errors, improves forecast skill, and reduces overconfidence. It's this notion of reducing overconfidence is critical in terms of using forecasts to make decisions. If you can't be reliable, if you're totally overconfident, you say there's going to be this huge El Nino and you're wrong too often, then people are going to doubt your forecast. It's a little bit like crying wolf. So this is from the Climate Historical Forecast Project. I want to show you results quantifying that a little bit better. This is from the NMME project. This is the North American Multi-Model Ensemble Project. And you'll hear me say NMME really fast. And it sounds a little bit, I tell this joke all the time, it sounds a little bit like I'm saying enemy. Hey, I even get a little titter every time. It's not my enemy, I assure you. This is one of my favorite projects to work on. But I do speak fast. And this picture is called reliability. This is really digging in and getting very quantitative about that notion of being overconfident, if you will. And so what we want for a reliable forecast is we want that red curve, that blue curve, and that brown curve to sit right on the diagonal, right on top of the diagonal in each box. And I show you all these boxes, and it's very complicated, so I'm going to try to boil it down for you. If those curves are tilting too much down, like it is where that oval is, that means they're overconfident. That means the model is saying that there's an 80% chance of there being a big warm temperatures, if you will, but it only happens 60% of the time. Okay, so that's not good. All right. So the upper left picture, that was the climate forecast system that NOAA was using. And so you can see a real clear indication for both warm and cold, red and blue, that there's a overconfidence. For brown, that's near normal. We just suck. We can't predict near normal. That's all I can say about that. Now, we have this multi-model ensemble, right, that we constructed to make sure it included all this model diversity, but it's exactly the same ensemble size. So if we go to the right-hand panel, the upper right-hand panel, you can see by that vertical bar there that we've moved those reliabilities up. So that's how much we improve or reduce the overconfidence by using multiple models, a diverse set of models, bringing multi-institutions to bear on trying to make predictions. And then the bottom panel is showing you by increasing the ensemble size. So this is quantifying that result that we saw in the previous slide in the sense that we know that half the improvement is coming basically for 2-meter temperatures over the northern hemisphere. Half the improvement in this reliability of the forecast, of this reduction of overconfidence, is coming from multiple models, the diversity of models, and half is coming from the fact that the ensemble size has gotten really large. So both of those things really do matter. Okay. So then this raises the question. This raises two questions. So the first question is, how many ensemble members do we need? It's a reasonable question. What's the right ensemble size? Unfortunately, this depends. This depends on what's being predicted. So what I'm showing you here on the left is an interesting recent result, and it's basically arguing that when we look at how well the model predicts itself, we would expect the model to predict itself really well. But actually, in this particular case for the NAO, the model does a better job of predicting nature than it does in predicting itself. That's amazing. That's truly amazing. We always thought that when we did these model predicting itself, it was an upper bound to how well we can predict. But it turns out, in this particular example, it's not. The lower bound, which is how well we can actually forecast something that can happen, is actually higher than what the model thinks. So this is actually pointing to a fundamental problem with either how we do the forecasts, initial conditions, how we set this whole problem up, or as a fundamental problem with the models themselves. Again, WCRP, International CLIVAR, USGCRP, US CLIVAR saves our bacon. So what we have here in the panel that says D, although it's just the second panel, this is actually sorting out which is it? Is it the models or is it the forecast problem? And this is saying everything in that light blue area is saying all of these models from CMIP6 have exactly the same problem as this particular forecast model on the left. In other words, the models don't have the right signal-to-noise ratio. So it's not a prediction problem, it's a model problem. Okay, so this prediction exercise, this multi-model prediction exercise asked the question of how many models. We got diverted by a very important question, how many ensemble members do we need? We don't really have a clean answer. But then the question is, how many models do we need? We still have to answer the question of how many models do we need? How much diversity is required? So this is looking at a skill metric. It's a probabilistic skill metric. It's called Breyer skill score, again for northern hemisphere, so that's everything north of 23 degrees, 2-meter temperatures over the whole hemisphere, March, April, May, February initial condition. And this is the red boxes correspond to warm terciles, blue cold terciles, green that near normal tercile. Again, we can't predict normal. This slide, by the way, is from one of my colleagues, Emily Becker. And what this shows, if I look at this picture, what this shows is it looks to me like we need, I don't know, 3 or 5 models. So that's pretty good. We have a heck of a lot more than 3 or 5 models available to us. The problem is we don't know for any forecast, for any initial condition, for any lead time, for any variable, for any situation. We don't know which 3 models are the right 3 models. So we tend to have to use a lot more models. And this picture is, let's just look at the left-hand panel because time is running short. This is comparing a probabilistic skill score. It's called the rank probability skill score, and it really just measures how well the models capture the observed probability distribution. And what this is showing is that if you have 7 models versus just 3 models, and the choice of the 3 models is carefully chosen. But what you can see almost everywhere except the central US, of course, almost everywhere in Florida where I live, central US and Florida, almost everywhere, 7 models tends to be better than 3 models. And almost nowhere, right, almost nowhere, 3 models will be better than, there's a few spots, 3 models would be better than 7. So, you know, we can't have 100 models. 3's not enough. Is 7 enough? Another example of how US CLIVAR activities and also WCRP activities are driving forward interesting science questions. So this picture is a really goofy picture. When I first saw this, I really had a hard time getting my head around this. And this is from this sub-X experiment that my former postdoc Christina was my former postdoc, so she's making me feel very old. My former postdoc talked a little bit about this sub-X experiment. And what this picture is, it's a new metric. It's a sort of hot off the press metric that was developed specifically because we have these model experiments. It would never have, no one would have ever thought of this metric, and it's a very clever metric. Tim Del Sol and Michael Tippett came up with this metric. It never would have happened if those guys were not looking at these multi-model forecasts and asking the question, how do we decide if these multiple models are improving the forecast skill? And so what this picture is showing you is from the sub-X models, and it's showing you how, if I take the NOAA operational system and I combine it with one of these sub-X models, how does it do just with CFS alone, the NOAA national model, operational model all by itself? And if the curves are above the page, above the the plume, the black part of the plume, the black line, then the NOAA operational model is better, and the additional model is not providing any information. As you can see, as forecast time goes on, all of those additional models are pushing outside that plume. And in fact, the one that's furthest outside the plume is the multi-model combination. So that there's a definitive showing that multiple models are doing a better job of capturing the observed phenomenon on these sub-seasonal timescales. We've known this for quite some time on the seasonal timescales. This is first starting to emerge on the sub-seasonal timescales. And these new techniques for evaluating forecast skill are really powerful and compelling tools. Holy smokes. I'm like a third of the way through this. All right, I talk too much. This is an interesting, it's not just predictions. These predictions provide a database, a collection of tools that are a test bed for evaluating future model improvements, future models, but also really digging into some important questions. So in this particular plot here, we're asking coupled feedbacks. Do coupled feedbacks matter when you're trying to talk about the MJO initiation? And this particular picture is from this important field campaign, this Dynamo field campaign in the Indian Ocean. And the big panel is the observations of rainfall in the Indian Ocean along the equator. And this is during this MJO event 2. There were 3 MJOs during this Dynamo field campaign, and this was MJO 2. What's interesting about MJO 2 is it's labeled as a coupled MJO. So now there's this whole diversity of MJOs coming out, these Madden-Julian oscillations. There's uncoupled MJOs where the atmosphere can spontaneously initiate without really talking to the ocean. There's coupled MJOs where the atmosphere and the ocean talk to each other, and there's probably a lot more different kinds of MJOs. But this MJO2, everyone's decided is a coupled MJO. The 2 right-hand panels are subsetting those sub-X models. The top is all the sub-X models that just persist the SST. They don't predict the SST. They just predict the SST anomaly. And then the bottom panel is the sub-X models that actually predict the SST. And so when you have a coupled MJO, to be able to capture that coupled MJO, you need to be able to have coupled phenomenon. And so that identifies a forecast of opportunity, because it turns out they don't do very well at predicting the MJO at all when it's not coupled, either of them, okay? So it's a forecast of opportunity. If I know it's a coupled MJO, then I can have some confidence in that forecast. I'm going to skip ahead a little bit here just because I'm running out of time. So this sort of brings me to my second point, is it's a collaborative test bed that these multi-model ensembles and that WCRP and USGCRP are providing for us to make model assessments, to make improvements and improve understanding, all kinds of things. And I'll just show you one last picture. This is showing you from the NMME models. This is showing you the forecast scale of sea surface temperature. And the blue ovals are indicating regions where the forecasts are worse than climatology. You'd be better off guessing. You'd be better off guessing what the sea surface temperature is. And those regions all have something in common. something very important in common. These are eddy ocean, these are eddy-rich regions, these are western boundary regions. These are pointing to a serious problem with our models that we think we should be able to fix. And I'll stop there because I simply, look at all that great stuff. I simply ran out of time. I just want to leave it with, with that WCRP and USGCRP are so important. This is just a slide from a recent workshop on subseasonal to decadal prediction. They really are so important in supporting this collaborative environment where we can really pursue breakthroughs in science. And so, thank you to WCRP and USGCRP. I'll stop there.
Thanks. Questions? We've got time for one question.
I tried to go over by too much so there'd be no questions. I tried.
Thank you. I think this would require at least 100 questions, but anyway, two, if I may, in one. The last slide, last one, where you showed us that resolving the processes instead of parameterization to large eddies gives you actually counterintuitive result, which means less skills. I mean, the whole community is expecting a kind of, when we resolve finally the clouds and go to 2 kilometers, 1 kilometer, but you are saying this is going wrong way. So that's interesting. That's actually discouraging.
No. I want to be clear about this. This picture is indicating that we're not resolving these ocean eddies, and for the fact that we're not resolving them is
okay.
So they're unresolved here.
Okay.
And it's really pointing to the fact that we need to resolve them because we'd be better off guessing.
Thank you. Okay,
Yes.
that's the okay. Now, the other one, if you listen through the presentation, which was excellent, I would like to take these glasses which you use for this presentation and to sort of give us further assessment about what we are doing now in CMIP. Because we are doing basically everything which you say we should not be doing. I mean, I'm just using this expression in the black and white thing. So okay, you understand my question.
I don't think we're doing everything we shouldn't be doing. I think we're doing lots of good things in CMIP. Don't get me wrong. I think CMIP is critical infrastructure in terms of evaluating models and event attribution and understanding climate change and prediction. But I'm very impatient, and I do think we do really need to push the envelope in this seamless notion. For example, I don't know why we can't have 5 models that run every single day out to the mid-century, 200-member ensemble, very high resolution, that would then be available to everybody to look at for subseasonal predictions, seasonal predictions, climate change, decadal prediction, process understanding, biogeochemical cycles, all of those things. I don't know, fundamentally, I don't know why we haven't come together to just say we're going to do the big problem and make sure we provide that for all of our scientists. And that's a little bit hard for me to be patient about.
Thanks. So the final speaker in this session is Jean-Francois Lamarck, and he's the director for the Climate and Global Dynamics Lab at Ncar. His talk is about linking predictions and projections with societal needs.
Good afternoon, everyone, and thank you for being here. So this is the last talk. So I actually thought that, and these were really great talks before me, and really good introductions to basically what do you do with those models. I actually would like to take a step back and actually start thinking about what are those models, because I think sometimes there's just the push of this is the model, kind of like the gentleman who left, unfortunately, but his point was like, we use those models, but sometimes we don't really know how those models are built and how we should use them. And I think part of my discussion here is what are the models, how do we use them, what are they for, and what are limitations, how do we discuss and understand that. And so this is if you want to really look at it Earth system models, in my opinion, and this is very much biased from my own experience of looking at global Earth system models, so bear with me. But the idea of Earth system models is really to integrate everything we know about the laws of physics, thermodynamics, and our understanding of all the other processes that we feel are important, which means that there are all those processes that we feel are maybe not important and are just completely bypassed, and maybe completely changing our understanding of what the projections or predictions will be. I think it is still, especially with the angle that I was asked to talk about, in the current CMIP6 class, and a lot of what has been discussed here prior to me is relevant here. We are still looking at things at a very coarse resolution, probably around 100 kilometers, 50 kilometers, both atmosphere and the ocean, which has very strong limitation of the processes that can be explicitly resolved in such models with a time step of 30 minutes. So then if you start looking for extremes, for things from the real world, you have to start thinking, okay, if we're going to be looking at projections, how do I actually put my head around looking at the model results and making sense of that with societal needs in mind? And through funding from the USGCRP, a few years ago, a few of us, and some of them are today in the room, we were like, there's a strong drive for high resolutions. And then which of course makes for beautiful pictures, but is there actually additional information? And how do we know that there is actually additional information? And how do we use that additional information? And when do we need high resolution? This was one of the outcomes of the discussions that we had in Aspen for a week. But we actually do want high resolution because some of the fine-scale physical processes are difficult to parameterize. But also, the decision involves planning at fine scale, especially if you're in complex terrain, right? So what do you do if you're actually trying to do conservation in coastal regions, and what you deal with is 100 kilometers, right? So how do you actually go from all that we've been discussing, all of CMIP6, how do you actually go and use that information? And then it's even further true if you look at specific impact models, like hydrological models in complex terrain. Two things also that I just want to make sure that we're on the same wavelength. Projections are actually usually letting the model run. And we had beautiful examples from Ramaswamy's presentation of some of the things that are done with the model. You start in 1850, you have pre-induced control, and then you run the model continuously every 30 minutes, solving all the equations of interest, using just a few external forcings. Those are the only things that are driving the system. The anthropogenic emissions, volcanoes, solar variability, greenhouse gas concentrations, land use change. And to me, this is an amazing achievement that with all we know and just the specifications of those things, we can actually reproduce the 20th century in a lot of ways. Prediction is just exactly that, except that once in a while we specify the initial state of at least the ocean. One thing I really would like to emphasize is the use of ensembles in our understanding of climate change. And to me, that probably has been one of the key elements over the last 10, 20 years of redefining what do we do with climate science. And so this is an example of the type of experiments that people do. You run a model in 1850, in this case until 1920. 1920, you stop the model, you say, I'm going to change the temperature everywhere by 10 to the minus 14 Kelvin. That's Ensemble 1. Ensemble 2, and you will do 2 times 10 to the minus 14. and then you put 40, 50, however you want, how many ensembles you want. And those are the only things that will change between all those simulations that we have here. Globally average, it makes no difference. The mean of all those ensembles basically follow the same trajectory because they're forced by those very few things that are changing. And what is really important is this. If you look at different ensemble members, and there is 9 of them here, and this, you're looking here, this is just one measure that we can use. This is the linear trend of the wintertime surface temperature over about a 25-year period, which you would think is something that should be pretty robust to something that happened 50 years before. And yet, the information that you get out of the models, which do represent our best understanding of the way the climate works, is that the variability is extreme. If you focus, say, in California, for example, you look at this ensemble members and you get in the blue. You get here, you're in the red. Without the use of ensembles, there is no way we can actually identify any, with any sense of range of values associated with something as what should be robust as this, which in essence has really put a huge constraint of what the climate models or Earth system models can or cannot do. We are forced to use something at 100 kilometers because we would like to be able to do one simulation. Instead, we have to do 10, 20, 40. And so this is something that maybe is not completely fully appreciated, but the constraint of what the system is, and Ben's point is actually really clear that there might actually even be more noise, or the noise that the models might not be completely understood. So it is not clear that this, and this is only one model, and different models would probably do something very different. So again, what is in the essence of an Earth system model is to answer questions. The goal of the model is not to reproduce the 20th century. That is kind of a really boring exercise that we just do so that we can show that the model actually mostly work, and then there are all the analysis that we can do to justify using the model in its present state. What we want to do is to say, if you have this, and this is from the most recent global climate project, if you have this scenario or this scenario, what are you actually expected to see, knowing that there is that huge variability of just changing the initial condition by this little. This is just something that I've done a lot of research on aerosols in general, and to me this is also when you start having the link between what the tools can do and what policy relevant questions can be. And this is a very specific and very isolated. What would be the role of anthropogenic aerosols versus greenhouse gas over the 20th century? If you don't have a model, you cannot answer those questions. But then you can start looking and try to attribute those changes without the aerosols as we know how to do it currently, and then the greenhouse gas would have led to a much warmer world than the present day. And so to me, this is again what we're trying to do with those Earth system models. This Earth system model is then used, and this is where USGCRP and all the agencies involved is critical. It can then be used in the national climate assessment and things along those ways. As I try to indicate, there is the limitation that we have to go to scales that the model can only handle about 50, 100 kilometers when you're using for climate prediction or projections over long time scales. So how do we go about reaching the spatial scales of relevance? And this is, for example, what it would be in 2100 over Phoenix. And so you're trying to go from what that Earth system model was trying to predict with all its variability into something that is at the sub-scale of a city. And so there is a huge amount of information that has to be distilled, that has to be somehow processed to try to downscale. One thing that I think is very promising is that we can actually now starting to develop models that will be able to address directly to represent the details at a much better scale than what we do now by using regional refinement. And that's where I see very much a need for, in a comparison, multiple groups are able to do this. How do we know how to do this well? Because this might be the key to really help doing those prediction within a single framework and start reaching the spatial scales of relevance. At the same time, just going with the brute force of bringing information by just increasing the resolution might not be the most useful thing. And this is a paper that was published a few months ago from someone at Ncar who actually tried to use what I would define as a combined dynamical and statistical approach. If you have a model that has 100-kilometer grid, then you would expect, at least hope, that the large-scale patterns associated with such a model would actually be represented somewhat accurately. What this shows is that if you try to look at precipitation, and these are decadal prediction experiments, similar to what Ben was describing, but on the decadal scale. This is what the model would be doing. 0 scale in predictability. What Isla did is to say, if you look at the observations, if you understand the real world, you know that there is a really good correlation between modes of variability in the Atlantic and precipitation over the Western UK and Portugal. Why don't we use that information? And now we just use the model and its ability to do the large scale. And then the combination of those two is actually giving us really strong predictability over multiple years. And so this is, to me, where now we have to start thinking and bringing different communities and different approaches to solving the issues of prediction, predictability, and providing the information that's going to be useful for society and the people. So I think the critical part in all this is we have to, and this where some of the things that I have done within USGCRP and others, is really the communication of the needs and the limitations. It is too easy to say this is a beautiful simulation, 3 kilometer, go at it, it looks beautiful, it has to be right. So, and the key element that I think we try to identify, and the first author is here in the room, so if you want to ask him questions, is the definition of really what we need to create. And I think this is where USGCRP can be critical, is to provide the framework to make the connections between all those boxes here. And I've only touched upon basically 2 or 3 of those, but how do we go from scenarios to all the way to decision context is by creating those boundaries, creating those connections, and the feedbacks. This is not a passing the baton to the next level, but it's really providing a framework for people to interact in both directions. And so this is all I have, I believe. And so with this in mind, then we can start looking at what USGCRP can provide then to the broader community and start looking at connecting all those elements that I tried to highlight. Thank you.
Thanks. Questions for JF?
Thanks, Jean-Francois. I'm Margot Klein from the University of Colorado. So on Monday night, I was at the town hall for WCRP, I believe that's the acronym. And it was the very, very end, almost 8 o'clock, and someone asked just a quick yes or no question to the panel, which was, do you think we understand enough to implement solar geoengineering? And every single one of them did a very short no. And so I would like to ask you, or anyone who is also speaking today, what areas would we need to improve in either our scientific understanding of the climate system or in model capabilities to feel more comfortable with actually moving forward in possibly being able to implement solar geoengineering?
Wow. Thanks, Margot. So this is the, and I'm guessing that the question, the angle that you're asking is maybe more about solar radiation management and maybe sulfate aerosols. And to me we have a certain understanding because we have volcanoes, we have something that looks similar to what would be the release of sulfate in the stratosphere. There's a lot of aspects that we don't know about the difference of having things coming out of a little plane and what comes out in a very different environment when there is a volcano. So I think there is a bridging of scales that needs to happen. Without that, I think there is just a lot of uncertainty of what such release would be. I think the big picture, maybe we have some sense. A lot of has been done with limited ensemble size, limited multi-model analysis. And I think that's going to be a key element to make sure that whatever consequence that we try to identify, we have an understanding of the robustness of what those results are.
I have a quick follow-up question, which is if you happily had unlimited resources financially or in terms of computer speed, say because this is the idea of all these organizations coming together, is there anything specific you would tackle in terms of computer resolution, or are there scientific questions we still have remaining on how the climate system works that would be relevant? So
we've actually, people at Ncar and others have started a consortium, a modeling consortium with the first aspect has been on the solar radiation management and stratospheric aerosols in particular, and to really try as a larger group of people to try to identify what do we think are the low-hanging fruit, what can we do to help the National Academy of Science and maybe the United Nations Environmental Program. In those discussions, the discussions are happening. I strongly feel that as a scientist, we have to provide the necessary framework to answer the questions that are, if not being posed right now, but it will be posed very soon, and it would be really detrimental to possibly the whole world if the scientists were not involved in the discussion.
Context, recently Secretary General of United Nations Guterres asked 3 agencies, UNEP, WMO, and UNFCCC, to do a quick assessment of the needs, how to tackle the knowledge base on the climate technology. So this is now happening. It's being discussed as we speak in Madrid informally, and so somewhere between now and June, such a report will come out, which will be no more than just state-of-the-art knowledge and proposal to community to tackle things which we are talking. So it's happening, at least in the initial stage. I must say, when Secretary General Guterres understood 1.5 special report, in which he understood that we need to go to the negative emission, which he didn't know before we explained to him, this discussion popped up very, very, very heavily. So that's actually connected to the 1.5.
Thanks, Pavel.
I'm Dave Jackson, a seismologist, and I came to this session because of the word prediction. And it's not hard to imagine why I'm interested in that. But what I sense in all the papers I've heard is that you're dealing with a problem that's common to every section in AGU. How to express your models in a way that they can be evaluated in a more quantitative and rigorous way. And how can you combine the information in different models using ensembles to get a better fit? And our models in earthquake forecasting are a bit different in character. We have point processes and you have time series and so forth. But nevertheless, I think many of the statistical questions are the same. The need for specificity in the model to say what exactly is it that the model is meant to predict, and to describe, well, what are the assumptions, the initial conditions, and so forth. And I would suggest that maybe we might try to have a joint union session sometime next year or some other time in AGU to talk about these kinds of problems, and really to emphasize the need in the sciences to make testable forecasts. I've sent some messages using the AGU app to a number of people who've spoken. I'll send one to you too. You know, with my email address, and would love to have some communication about
Send me
ways that we
directly
can-
to my email, because I may not look at the app after tomorrow.
Okay, well, we'll talk in a minute. I think and,
Maybe.
we can exchange emails.
It sounds great. Thank you.
Last one? Chuck
Yes,
Akarainen.
last
Usually
one.
it's the first one.
Yeah.
I couldn't get here quick enough. Chuck Akarainen retired from EPRI. I liked your explanation of how you do the ensembles by adding 1 times 10 to the minus 14, etc. Have you done the experiment where you add 0 times 10 to the minus 14K, but instead of adding 1 plus 2 in every location, you add 2 plus 1? In other words, is the model bit for bit accurate depending on the order in which the calculations are done?
Oh, no. No, that is not. Well, it is, it depends on the level of optimization that you get on the computers. If you get the compiler to just look at the code and make a run without trying to reshuffle, then it will be bit for bit. If you start going to optimization levels that are too high, then they start changing the loops, the loop orders. Then it's not going to be bit for bit. If you force the operations to be, it's possible that it will not be. Otherwise, the models are being tested all the time at all the modeling centers, such that they're fully reproducible within one system. If I stop it and restart it, it will be exactly bit for bit. Yes.
All right, I suggest you guys go off, get a beer, and
Yes.
discuss this more.
Thank you, everyone.
Thanks to all the speakers again. Thank you.
Thank you.